In this lecture, we finally get to the two-sample t-test, one of the most basic statistical tests, one of the first tests that you learn about in a first semester stats class, and we finally arrived at discussing this. But we've done so much work with the t-distribution, this is actually a fairly short discussion because mostly the t-test is just a way to look at two samples and think about how to convert those to something that's going to be t-distributed. So we have your basic form of the t-test, which is with unequal sample sizes but equal variance. Right? And so you have two populations, like maybe you have a population of mice with cancer, a population of mice without cancer. You want to see if something is different between them. You calculate the mean for the first population, you calculate the mean for the second population, and you take the difference between them. The null hypothesis is that these two means are the same, right? That x1 equals s2. So we know from the form of the t-distribution that it has to be some sort of difference in means divided by some sort of weighted standard deviation. Now remember, this is a standard deviation that we're estimating from the data. That's what's going to make this t-distributed. But in this case, I have two samples, right? So I have to have some kind of way of figuring out the variance from the two samples. So there's two ways to do this. One is going to be, it turns out, the inferior t-test, which is assume equal variance. But it turns out that we can actually have a better t-test where you can drop this assumption of equal variance. So if you have a weighted average, this assumption of equal variance, you basically have the variance in sample 1, the variance in sample 2. We just weight the averages and then make an appropriate correction for the sample size, right? What will turn out to be the better test is to just let the biggest variance win, right? So instead of taking a weighted average, you have this sort of more complicated formula where right the smaller variance here, right? If this is a really big variance and this is really a small variance, the small variance will drop out and we kind of let the biggest variance win. The only complicated thing with the t-test that does not have the assumption of equal variance is to calculate the degrees of freedom. That's fairly complicated. It's given by this equation here, and we're just going to accept this equation and state it without proof. Okay, so let's take a look at why you probably always want to take the default t-test, which in R is the t-test with a drop which does not have an assumption of equal variance. So here we just have two samples, right? I have sample A and sample B. In sample, they both have a mean of 0. So sample A is standard normal distributed. So I take 5 samples from the standard normal distribution. Sample B, I'm taking 5 samples from with a mean of 0. So the mean is the same, but the standard deviation is 10. Okay, so the means are the same, but the variance is different between these two samples. If I don't take the default in R, if I just say t-test A, B, not taking the default, that's the equal variance t-test. That's this one here, right? And we can see that this test breaks. The p-values come out too small. All that I have to do to fix this is to let the highest variance win. So not take the weighted average, but let the highest variance win. I can do that by just typing t-test A samples, B samples, $sign p-dot value. That's what we've been doing in the last two homeworks. Or I could explicitly say that I want the variances to be not equal and say var dot equals is false. And when I do this, the uniform distribution is restored. So this raises the question, should we just always use the t-test with an assumption of equal variance? And the answer to that question is basically yes. There's really no reason to ever say var dot equal equals true versus var dot equals false. We should always just basically let var dot equal equals false, or just take the default t-test in R. And so here we're looking at sensitivity. We're looking at the p-values between the two tests, and we can see that the p-values are pretty similar between the two tests, right? So we gain protection from this assumption of equal variance, but we essentially don't lose anything by just having var dot equals false or just using the default in R. And so this is probably why var dot equals false is the default t-test in R. And this has actually been argued in the literature. This paper that was published coming up on 10 or 11 years ago now, basically arguing that that you should just always use the form of the t-test which doesn't have the assumption of equal variance. So t-tests come in two flavors. There is paired and unpaired. You can specify whether a t-test is paired or unpaired in R with the paired option. So by default, you have unpaired t-tests, but you can say paired equals true. In a paired t-test, the two conditions have to have the same number of samples. And what you're actually testing is that you're using one sample as a baseline and then looking to see whether the other sample has changed. So actually, the t-test has this formula, the t statistic that you calculate has this formula. This is the difference. This is the average difference between the two samples. And what you're testing is whether this average difference is different from some constant, and that constant is almost always 0. So this mu 0 here that has the average that is a constant. That constant is almost always 0. So the test is that this value is not different from 0. And just to make that a little bit more concrete, just imagine you have 4 mice in an experiment. You have weight before treatment and weight after treatment. So the pair t-test is often used for these kinds of longitudinal samples where you have patients before and after a drug or after treatment. And so these are the same mice, right? And the question is the weight after treatment the same as the weight before treatment? And so the way this pair t-test works is it's looking what this test statistics that's calculated is the average difference between these samples, and we're testing whether that average difference is the same as 0 relative to the standard deviation of all the differences. So this is very, very easy to do in R. Again, all that you have to do is say paired equals true. Notice that often there is no requirement that we say paired equals true. So we could just say t-test AB. That will just make a non-paired test. And a non-paired test, the null hypothesis is that this distribution is the same as this distribution. Okay, that's subtly different from a null hypothesis. So that's the unpaired test, that this distribution is different from that distribution. That is subtly different from a paired test, in which the null hypothesis is that the mean of the differences equals 0. In general, the paired t-test usually has increased power relative to the unpaired test, so you have more of a chance of picking up a true difference. But there are times when both tests can be valid. And again, if you don't specify in R which one you want, you're just going to get the unpaired test. You have to explicitly specify to R that you want the paired test. Very briefly, I'm not going to go over this in the lecture, but for your reference, if you ever need to implement the t-test in Java or another language, it's actually quite easy to do. There's libraries such as this open source library, and you can go to this GitHub and find all of this code. There's libraries such as this open source library that implements pnorm, and once you've implemented pnorm, it's quite easy to get to the t-test. So again, just for your reference, there's libraries in Java for pnorm, PT, sort of all of your friends that you can have in R, you can have in Java. Undoubtedly, they're in Python as well. So this is just for your reference in case you ever need to implement these in some language other than R.